I think we can probably get started. Whenever you're ready, take it away.
Hello everyone. So today I'm going to do a refreshing for you about Numpy and Pandas if you already know them, or if you are new to them, we're going to start from scratch talking about them, Numpy and Pandas, the differences between them, and also like the differences between Numpy and list and when to use which one. Okay, like originally in Python, if you want to create a list, you have to define a name for it, then the equal, then the square brackets, and then you have different type of data, right? So for example, we could put 1, 2, 3, 4, 5, and then we run the shell in Jupyter Notebook, and then we can create new cells, and then in Jupyter Notebook we don't need to print. In Python we need usually a print to print the value, but in Jupyter Notebook we just need to write the variable name, and it will just print the value of it. So this is how we create a list in Python. And a list also can have different type of data. So we can have integer, a float, a Boolean, or a string, or a different list also. Right, and this is also works fine because the list can have different type of data. And we can have different operations. And the reason we want to use list or next a number array is because we have one different or large data, and we want to work on them and store them in one variable instead of like having, let's say, variable 1 equal 10, variable 2 equal 20, variable 3 equal 30, and so on. Instead of having like 1,000 variables, we just create one variable and we store all our values inside them. Let me, I can't hide it. Okay, and so this is why we mainly use a list. There is also a number array. And array is similar to list that where we use both of them to store data, and we can update and change the values inside the arrays and the list. We can also expand both of them, and we can also extract values from them, and we can go through a loop using a loop through the list or an array just to search through values or operate on them. This will go through now, but there are some few differences between them that when you use an operator, it can operate on each value inside the array, but inside the array, or when you use an operator like plus, minus, or multiplication, it will operate on the whole list as one object. And arrays can only have one type of data, but lists, as we have seen now, they can have different type of data. Okay, so another thing is that arrays are fixed size, but a list we can update it. Do you have an idea, like, for example, for arrays, there's a function that can update the array. If we start with a fixed size, we can update it later with a specific function. Could you think of an idea why, although we say it still fixed in size, we can update or increase the size of array? If you have any idea, you could write in chat or unmute yourself. Okay, so the reason behind this is it does not increase the size, and the array is fixed, but what's happening is it creates a new array with the new size and put all the new data inside the new array and then delete the old one. Okay, so to work with NumPy, first we need to import it. And NumPy is a large library of functions that has been defined, optimized, and checked by many people before. So we don't need to, most of the functions that you could think of most likely are there to operate on an array, like sorting them or changing the dimensions from one dimension to dimension, or slicing through them. There are many functions, or like, for example, a convolution. There is a function for that, which is, that you most likely seen when you use image processing on on arrays. So first, as we seen before, we want to define a list, X list and Y list. And then to do the same thing using NumPy, we use the name that we used to import the array. So there are different ways to import NumPy. Either we could say from NumPy, we import a specific function, right? Or we could import the whole library of NumPy, and we write import NumPy. But to reduce the time when we write or use NumPy, we give it a short name. So it's common to use the name as NP. So NP is a short for NumPy. It's better to use the same thing. So when you work with other people on the same project, most likely they will use the same one. So it's not to confuse other people or make it easier for them to follow you on the same code. So when we imported NumPy, now if each function inside the array, we can call it using then the NumPy name, the short name, dot, and then we use any function that inside. And here we are using the function called array, and a nice feature in Jupyter Notebook that we can see once we highlight it or just hover over it, we can see the documentation for it. And for example, similarly, when we hover on the function array, we can see that it is a function, the definition of it, what it takes, and the data type, and many other values, and what it returns here. So we are using the same thing. So np.array, then we open the function brackets, there is curly brackets. Then we give it a list, and this list will use the same thing to define the array. So once I call this one, then if I want to check, we have X list. It prints me the list, but once I write X, it will tell me that it is an array and the values inside are these ones. And so the first thing we said, so before we said that the operators like plus and minus and multiplication, they don't work on a list because they work on the whole list as one object, but on array as on each element. So now if we print the list multiplied by 4, and now then we will do the same thing but with the array, and then we use the division of X, the array over 4, and the same for the list. Once we call it, the first one will give me the list. It will repeat the list 4 times. So 1, 2, and then 3 and 4. But for the array, it will multiply each element by 4. So 4, 18, 12, and 16. Similarly with the division with the array. But for the list division, this will give us an error because the division is not supported. You cannot just divide one object and take part of it. So we need to always look at the error. It says here the type error. unsupported operand types for the division, list, and integer, that the division does not work between a list and an integer. Okay, now another thing is a good thing of a list and array that we can, if we have like a large amount of data, let's say a mass of stars, and we need to go through them and work on them, we can use a for loop. So we write a for, then my variable, which will change using the values one by one of the list or the array, and then n, and then my list here, the list or the iterable, which is the list here or the array, and then we can inside the loop have any action that we want to do. For example, measuring a distance. Let's say, for example, the x-list here have the coordinate of my star, and we want to find the distance from the coordinate of the star, then we want to find the distance from that star to a specific star. We can use this to find the distance of all the stars to a specific one. And similarly for array, it's the same syntax. And once we call it, what will happen is it will take each value inside here. If we print it, the values, so it will take, we'll say val equal 1, and then it will print val, then val, after the end of the first iteration of the loop, it will go and update the value of val to the second value, so val equal 2, and then print it. And this will keep going until the end of all the values inside the list and array. Do you have any questions so far? Then I think it's very clear, or nothing at all. Okay. Then for array and list, we can have like a multidimensional one. For now, here we defined one dimension. We could define multidimension as X list 2D, let's say. And the way to define it is we have 1, 2, 3. We have to define each element inside the list as another list. So we have one list here, then similarly, we have another element inside the list, which is a list. So a list inside the list. And if we do this, now we can, let's do this. So it will print us that the first element in the list is a list, and the second like this. And what's happening here is we have a two-dimensional array with two rows. So this is the first row, the second row, and each row has 3 columns. Similarly, we can do this with an array. And as we said before, in Numpy, there are many functions that are predefined, and one of them is the random. And the random is used for random number generation. And inside it, we have a function called uniform. And as we see, we do a sample, the definition says it draw a sample from a uniform distribution. And we can use this to generate either one, to get one value, or get a 1D array, or a 2D array, or a 3D array. And this is very helpful when you work, when you need to randomize some data in your let's say, for example, you are using machine learning to train some model, but then you generate some data that it is two values, then you use some random number to offset the values to train on them. And in this case now, we tell it that the size that we want is 5 by 5. And once I run it, it will give me an array 5 by 5. So we can see that here it says an array, and it has 5 rows, as we see, and the rows are separated by a column, and then a comma, sorry, by a comma, and then inside each row, we have 5 values separated by a comma. And yeah, so we can see that here, 1 row, 2nd row, 3rd row, and 4th row. So we can also use the iteration inside the for loop to iterate through them. No, so this is called a 2D array. There's a question, is this a 5-dimensional array or 25-dimensional array? So no, this is a 2-dimensional array with 2 dimensions along the rows. Here along the rows, this is the first dimension, and along the columns, this is another dimension. You could generate 3D or 4D arrays in Numpy, but it will not be easy to see them here. They will be repeated, so like it will have the first element of the 3D array as 2D, and so on. So it will not be easy to visualize it. So now if you want to iterate through them, if you want to iterate through the array, as we said, the array is an array of arrays. So the first element is an array. And so if you want to look at it, it's a 1-dimensional array where each element is a one array of 5 elements, like a nested array. You could think of it as a nested array. So if we try to loop through them or iterate, what will happen is it will take the first element and print it the second element, and so on. So if we do as we've done before, for val in y, which is our array that we have generated here at 2D, there's a question, what does the dot uniform part do in the random array? So the uniform here, there are different ways to generate random numbers in Numpy, and one of them is the uniform function, which will take the value from a uniform distribution. So like there is a uniform distribution, a Gaussian distribution, or different distribution that you want to take the value from, depending on what you want to use them for. Yeah, so if you want, I think if you let's start to have a quick look at the random generators. We have uniform distribution, normal distribution, uniform distributed floating points, uniform distributed integers, depending on what you want to generate. There's a binomial distribution, beta distribution, exponential distribution, gamma, geometric, and so on. So it depends on like the problem that you're working on and what kind of random numbers you need and the problem you have. Okay, so we're going back now. We are iterating through the Y array. And once we do this, and if we print it, what will happen is it will print each element at one time. And we can do this in a different way, which is we call slicing. So for example, Y of 0, it will give me the first row. But if I want the second element with it, so from the first row, we want also the first column, we print Y0 and 0. So this will give me the first value here. If I want to say the second one, we just put this to 1. If I want all the columns, I could use a colon here, and it will print me all the values. And as we see, it's identical to here. Similarly, I could put the colon here, which means print all the rows. And if I want, I can say print the second column, and it will print me the values here. And you can see them here, 0.6144, 0.744, and these are the second column, but all the rows. This is what means here when we put a colon. So we could use this in a for loop that here we have, we're using the function range to generate the numbers of, let's see what it does. We have a range which will generate me the numbers between 0 and 5, and it does not include the 5. And then what we're doing, similarly what we've done here, we say, print me the first row and all the columns, and we are doing the same thing as a for loop here. But what we notice here is this is less readable, so you need to concentrate more to see what it's exactly doing. But this one is easier and quicker to understand. So sometimes you should go to something which is quicker, easier to read by others, so they can follow up or follow on your code, instead of this one, which is, it will do the same thing, but it's just more complicated. Another advantage of arrays is that we can apply conditions on them. So let's remember our array X. So our array X has 4 values, 1 to 4. We can apply conditions, which is like this. So we want to define a new value XS equal X, and then we have the condition that all the condition which is all the values inside X which are less than 2, and in this case it's just 1. Once we run it, we have 1, and if we put like X less or equal to 2, it will give me 2 values, and this condition will apply on all the values here and will give me these values. Now, once, yes, there's a question, is this masking? Yes, we could create a mask. Let's say mask equal X larger or equal to 2. And then we say X of mask, and it would give me the same thing. So it's a way, so a mask is where we define our condition and we just apply it. So we store the condition because we want to apply it on different arrays, and we don't want to keep repeating the same thing. Yeah, and then once you are working like with one array, then you want to start working on it. Sometimes you say, okay, I want to check my work. So you want to make a copy of the array and then work on the new array. So to create, it's common sometimes. So it makes sense that we say Z equal X, that now we copy X inside Z, but this it does not work like this in Python. What's happening is we are defining a new variable name, but it is pointing to the same array. So once we modify X, it will also modify Z. Let's just remember what X is, 1, 2, 3, 4. And now once we run this, we copied X and we made a new name for Z that point to X, and we updated X, and then we printed Z. Now we see that Z has been also updated. So we need to always be careful how we make a copy, and to do the correct way is we use a function called .copy. So because X is a NumPy array, we can use all the function inside NumPy by using dot to call any function from NumPy. So we use the function copy, and now we make a Z. It's a new copy separate from X. And if we update X, Z will stay unupdated here in this case. There are many functions inside NumPy, as we said before. For example, stack, which will create a horizontal array of a stack of all the arrays. Now, for example, we want to stack X and Z along the horizontal axis. This is what we get. But if we want to create them as different rows or a vertical stack, we can use a V stack. And once we call it, this is the output. There are different practices that you should try to keep in mind, that you always want your code to run faster. You could write the code to run in 1 hour or in a few minutes, and yeah, you want to always make sure that it runs faster. So there's a question is, why is the stack they are not separated? So stack in this so stack, because it will merge all the elements of X and Z as one array. So if you are merging two rows together, you will get a longer row. But if you are merging two, if you're merging two rows as together as a stack, you get a larger row. But for the vertical stack, it just stack them on top of each other. Okay. So another thing is if you are working when you are working on a complicated problem and you don't know if you want to use a loop or array operation, you could always start with a for loop because it's easier to understand and find the answer you want. Then afterward, you can start to simplify your problem using array operations. And loops are often more readable than list comprehensions. It's easier just to see what is going to happen. The second part of our topic is pandas, and pandas is basically like a table in Excel where you have different columns and you want each column to have one type of data, but all the columns are different types. So like, for example, you have the first column is the mass of the star, the second column is the coordinate, the third column is the temperature of the star, and so on. So where each column is a different type of data, but all the elements inside one row correspond to one object. And to create a table or a pandas table, we are using the library called pandas, and it's common to use the short name PD. And now, first, we want to create a series where a series is just one column inside a table. And in this case, we create a list with all the values, and then we use the function series. And just notice here, the series is capital dash. So we call the function and we give it the list, and it will give us our series. So the first here, the first column 0, 1, 2, 3 is the index of my values, and the second column is my values. And at the bottom, it will tell me the data type, and in this case, it's just float. So now we created one series, but a data frame or a pandas table is a group of series. So if we want, if we want to create a data frame, we have to put one or more series inside it. And to do so, we use the function called data frame inside pandas, and we give it my series, and we give it the column table. Like in Excel, each column has a name or a title. And when we do this, it will print it as a table. This is one feature of Jupyter Notebook, is that it's easier to visualize pandas or data frames. So we have the column title, and then we have the values, and then the index, which we can use to call a specific row. If we want to create other columns, we just have to give it the data frame name, which we used here, df, and then we give it the title of the new column and the values. And what we're doing here is we're using our original column here, samples, and we are operating on that column or series to create a new columns. And we're using here the integer division. Then we're using addition, and then here we are calling the values inside the column samples using dot values, and then we're scoring the values. And once we do this, we can see our table. And now we can see a table with 4 different columns, and each column has its own name. We can use it to call the values inside. And to save a data frame, we just use the name of it, and then a function called to 2_CSV, and we give it the file name .csv, and we can run it. And similarly, we can use read CSV. If we look here, now we have demo.csv, we have saved it here. And if we open it, we can see that it says here, put the columns name on the top, then we have the values, all of them separated by a column, a comma. And if we try to open it in Excel, you will see just a normal table. We are short on time. I need to rush for a second. So different practices for Numpy Pandas. So both Pandas and Numpy can do the same thing generally, but it's easier to use Pandas when you have a large data set of heterogeneous data, with different columns. But it is less memory efficient than NumPy. If you try to work with NumPy and you have different columns, then you have to remember which column corresponds to what. And each time you go back to work with that, you need to remember which one. So it's easier in this case to use Pandas. And when you try to combine different data sets from different sources, it's also easier to use Pandas because you have different columns. Are there any questions? Okay, if there are no questions, we can go now to the activities. Let's do the same thing as we've done before. We have you have the roles of navigator and driver. So you split between each other, the navigator and the driver, and we have two activities here. One, we want to show the differences in speed between NumPy and the list. And here we have an example. So a sample code, when we run it, it will create a list. And then inside the list, we want to add to each value, we add 1 and divide by 2. And then we want to use a library called time to measure how much time it took us before took us to update the values inside the list. And what we're doing here is we have T1, we register the time before and the time after. Then we output the difference between these two times, and it is 0.9 for each second. And so what you need to do is you need to change the for loop here with an array for array, and also change the length for so the library is called time, and there's a question, why is it called time to time? So the library itself called time, and then the function inside the library is also called time, and this function will return the current time in seconds since epoch fraction of a second may be present if the system clock provides them. So it's just a function with the same name as a library. So what we're doing, what you need to do here is you have the for loop, and you need to go use the same thing with the list and change it to array and use the same thing. But also you need to do it for different sizes. So at the end, you will have one plot on the x-axis, the size, and on the y-axis, it will be the time. So you will have something like going up like this, and the other is going something like this for a list and array. Okay, and the second activity, so for this activity, we will give you like, let's say 15 minutes. And for the second activity, maybe like 5 minutes or 10 minutes. So you just need to discuss between you, between each other, should we use a for loop or not in a scenario of multiplying each element in an array and so on. Are the activities clear, or is there any question?
I'll post the link too so everybody has it easily available.
Okay.
Awesome. I feel like we've got enough remote people for like 2 groups, and then the folks in person, you all can be in a group together. So I think the remote people, if your name starts with A, B, or C, go to group 1. And if your name doesn't start with A, B, or C, go to group 2. All right, I'm going to open the breakout rooms. All right.
Welcome back, everyone. How did it go? Do you have any questions, or what are your thoughts about the answer? It's okay if you did not manage to solve it, or you did not have enough time. Okay, then I will share how could the plot could show up. So this is one plot that will show you. You have 2 lines. The purple one is for the list, and the dashed line is for the array. On the x-axis, we have the size, where we have like equal size of array and list. And on the y-axis, we have the operation time, the time it took us to run our operation. And as we see at the start, the list is faster because for a small size, lists are more efficient than array. But as we increase the size, the arrays become more efficient. And yeah, so this is how would it come with you. Before, if you did not have the time to finish, just give yourself more time before looking at the answers and try to do it. For the second one, just type in chat quickly, like yes, no, as should we use a for loop for them? So like, for example, yes, no, mean yes for the first scenario, no for the second scenario, and yes for the third scenario. Would you like to share your thoughts? Okay, we have one. No, yes. And there's another answer, the opposite one, yes, no. Yeah, it's okay. So for the first one, when we started the lesson, we said if we want to multiply each element in an array, the operations or the operators support the array, so you can just write x multiplied by 10, and that will do it. Or you can do it the other way, like here, for example, but you don't need to. So in this case, both ways will work out the same, and then there is no need for a for loop because it's slower. For the second scenario, it's talking about a convolution. And a convolution is a matrix multiplication with another matrix. So in the case where we had 5 by 5 array, like here, we want to multiply like the first 3 by 3 by another array. So each element will be multiplied by another element. And on the first thought, like when you want to code a convolution function, you will do it with a for loop, that's fine. But afterward, you don't need to because it's already defined in Numpy. And so the function is already defined, you don't need to use a for loop. For the third one, it's talking about if we have 10,000 images and we want to apply the same function for all of them. In this case, we need a for loop because each one is independent of the other one. Each one is independent from the other one. And so we need to use a for loop, but because also they are independent, we could run them in parallel using for loop. And this you will learn about on another day. We have a lesson for parallel in Python. There is a question is, what is the defined function in NP for convolution? Yeah, thank you, Sarah. The function is called numpy.convolve, and I think I might be able. So nb.convolve, yeah. So it's this one. We have our array. Yeah, So we have our array and the array that we want to apply it to, and yeah, there are different ways. There are different options for it. So you just need to read the manuals for it. Are there any other questions? Okay, then I will leave you for the second lesson on Matplotlib with Maria. And thank you, everyone.
Thanks. Feel better too.
Thank you.
All right.
Yeah, so feel free to share your screen and take it away whenever you're ready.
Yeah, thank you for the optional lesson and for today. I am remote, but I'm feeling the excitement. All right. I don't see the questions, but I will periodically check. In this first part, I just have some PowerPoint slides. So it's almost midnight here, and my babysitter leaves at midnight, so we're gonna try. I know it's you had so many sessions, so you might be tired, but let's try and have some fun because it's plotting. So working with images and visualizing, which is fun. Matplotlib actually has this kind of history, like many other science softwares, that there was a paid software called MATLAB. Maybe you've heard it, especially used in engineering, and it's expensive, even though it does nice things for science. And they have created Matplotlib, which is free for us. So this is the meaning of the name. MATLAB creates a mat and then the plot for plotting figures and library for Python library. And here's a documentation web link. So its main agenda is to make figures, especially different kind of histograms and things like that. So I have used my MATLAB experience, Matplotlib experience is as any other Python packages. I'm a self-learner, starting from my master's degree. When I started doing astronomy, my supervisor said you have to learn Python. So I learned it on a job when I was working on projects. And I mostly work with observational data, 2D or 3D spectroscopy or photometry. So using just table data and visualizing it, I did do some simulations and continue to do, but it's also just how would the galaxy look if it was exposed X number of, seconds in a certain filters and stuff like that with certain noise. So this is where my experience comes from, and maybe you know more than I in certain things, so feel free to jump in. But here's where you can find the activity materials. If you go to the GitHub for this called Astro workshops, and you can do activity MPL, and we will be working mostly through the collab notebook, which is right here. It is IPYNB file, and the slides are here for your future reference. Okay, and we do have answer key, I think for all activities, which you can check out after session. I don't know if you are like me, but I have some humanities background, so I don't go crazy about software. I use it, but to connect to the software, it's kind of like what I have to do. I have to use software. Actually, both my parents were software programmers, so I grew up with these programmers, and I vowed that I would never learn programming, but then I liked astronomy, so my parents were correct. Now, any job requires programming, but this is one guy who was a neurobiologist, and I think he was a postdoc when he created this software, so that's amazing for me. So please, like any other software, make sure you cite and acknowledge, and here are some of the references for you. Yeah, their alma mater is University of Chicago, so another connection. Okay, so the very first tip, this is just based on my experience and some suggestions from other workshop organizers and TAs, but basically, whenever I have a problem of creating some plot that I have not done before, I just go to the library of images. Sorry, something is happening. Yeah, here. And just browse through Matplotlib documentation. They have a nice visual library, and pick the one that looks like what I need to do and then try to decode. That's one tip. And then the second tip, I have to tell you, it is might be confusing because there are two different ways of structuring in terms of writing the code and breaking down in the code language construction of figures. So it is a little bit like, I was thinking what it is like, maybe it is a little bit like using two different alphabets for the same language. For example, during the Soviet Union, a lot of countries used the Russian Cyrillic alphabet, like Turkish language, to write their words, but now some of them switched to Latin, like English type letters. So maybe it's something like that. It can get confusing because there is some difference. I'll move this. It's not letting me move some. Oh, here. So the names are implicit piplot interface and explicit axis interface. I use mostly implicit unless I have to do something complicated, and I go into axis. We'll see. We'll vote later. I want to know if you prefer which one or the other. Matplotlib, for example, to make this plot, you just write plot.plot after you import the library, and you give its values for x and y, and you get the plot here. So explicit deconstruct a little bit more of what's going on in a diagram. You have to call what's called like a figure instance after you import your library, a figure instance, and then you have to define your axis with x, or we can name it something else, but maybe you need to write a few more lines to, in this particular case, to make the same graph. Okay, and here are a few more examples of differences. If you want, for example, to set the labels for your axis, you do in a pyplot interface plot.xlabel, or axis interface is you should remind your code which axis instance you are talking about, and then you have to, instead of x label, you have to write set dash underscore x label. And this can be, at least in my experience, let's say I had a question what to do. I Googled it on Stack Overflow, I copied the code and it's not working. And it's very typical that it is because they wrote it in axis, let's say, and I was doing in pyplot, or vice versa. Okay. So what's going on the rest of the time? We are just gonna let you explore the activities. If I have divided them into A, B, and C in the collab, starting from some more simple graphs to more complex details about if you are an advanced user of Matplotlib. So you are free to choose your activity. You can start from A, or you can start from C, or you can follow them in sequence. And if you are walking fast, you can move forward. I just have a few more slides just to show you that in activity A, you just build a scatter plot. In activity B, we do a histogram. And then activity C has customization. So in activity A, I put a quirk a little bit that I want you to try to use both APIs to make the same graph so that you get the flavor. And in activity B, the key is that even though we are building a histogram, we are actually working with bars. So you might need to learn what is a technical vocabulary for that package. And in the rest of the tutorial, we dive into nitty-gritty details of Matplotlib. And if we don't have time, don't worry about it, because there is a detailed YouTube version from 2024 going into it. And you can always ask questions. My final slides are, because we are dealing with visuals, please keep in mind awareness about accessibility for visually impaired people, because there are many people who have color blindness, and there's different type of color vision deficiencies that people can have. And you can use, the biggest tip is, besides colors, other identifiers, such as symbols or patterns. And then I basically put in here extra links for you to explore if you are interested. I have a lot of people with visual disabilities around me, or other disabilities, so I'm very interested in this topic. We can chat. And Sarah suggested to include this color blindness simulator, which when you make a plot today or any other day, you can go ahead and run them through the simulators or contrast checkers to check how you are doing. I have some tips, do's and don'ts, which you can read later, especially for astronomy. And some more tips for accessibility and external packages, or the famous color bar to make pretty plots. So now you can go ahead and open the Colab notebook. It was right here in the day 1 activities, and you can try to basically rest of the session work and on these activities, and I'm here to help you.
I'll open up breakout rooms, and I think everybody remote can just go into one breakout room. So just go into breakout room number 1 to work on the activities. Does that sound good, Maria? Or is there anything else you want to say before everybody goes to the groups?
Just at any time during this session, if you decide you like one or the other, you can put vote which style you prefer. Did you prefer the axis instance, the explicit or implicit plt.plot, or any other? So you can put it in a chat and then we can assess. Thank you.
Sounds good. Okay, I'll open up the breakout rooms. There are some questions from in person, so.
Yeah.
Hi, Maria.
Hi.
I would like to ask some questions, probably more specifically for like plotting the relative positions of objects in the sky. Because our group is thinking about the project about like plotting the relative positions of like an asteroid relevant to the Earth, the Sun,
Yeah.
and the planet, so that we can know that if we're losing the asteroid because it's out of our field of view right now. Then for that type of visualization, I remember I have encountered like Matplotlib with some kind of 3D visualization or something that can help you like visualizing it. Do you have like any, do you know any like specific parts of Matplotlib or specific functions that could be helpful for that? Like,
so I don't have experience. It's such an amazing question. And there's actually several companies I know who work on similar things for asteroid, but I haven't. But it's basically tracking an asteroid and maybe in 3D visualizing if it's in your field of view. Did I understand? Whoa.
yeah. We're thinking about like retrieving the positions of the asteroid and also the other solar objects. And then, do that computation ourselves, like we know like how distant that is and what's the angle like in this coordinate system between those two objects.
Yeah.
And then visualize it. But then like right now, I only have an idea of like, yes, sure, a scatter point, like scatter plot could do some type of that job, but then I don't know, like, do you have
Yeah, I'm
some?
not sure how to capture movement of an asteroid. You can definitely plot any object on the simplified 2D array and deck.
Mhm.
So you have to make some assumptions and some calculations because, but that will give you an instantaneous position. I don't know, maybe they put a vector if there is a predicted. I don't know how to do like a moving diagram. I've never done it.
Oh, and it doesn't have to be moving too. Like we can just have snapshot of like,
Okay, a snapshot.
yeah.
Yeah. If you and this asteroid, have you looked at the data? Does it come with some sort of position on the sky, like array and deck? It's a degrees. Yeah, you just plot. Do I have a plot like this?
Is your main question about plotting on a sphere?
Yeah, like, or like, because we don't know like what the ending plot could look like. So just asking about, the possibilities in this package, like what kind of visuals we can do. Like say we have RE in deck or something, and then how it could look like.
Yeah.
Do you mind
You
if
can.
I?
Yeah, go ahead.
Oh, sorry. I was just gonna. I think I totally agree with Maria that I think one thing you could do is plot like in projected coordinates. So just plot the right ascension and declination in like 2D space. There's stuff in AstroPy for visualizing data on a sphere. So that could also be something that you guys explore. I haven't used it that much, but there's a nice package that makes some of these really nice like sphere visualizations. Let me see if I can find it and I can send it to you.
Thanks.
Yeah, no problem. Sorry, Maria, I didn't mean to cut you off. I was just trying to understand.
No, it's all right.
Feel free to jump in if you have more questions.
Yeah, in terms of logic, if you're have some area of view, you can define like reference point and then calculate separation between your reference point, let's say the middle of the diagram, and your object, and then if the separation angle. But it is beyond me, to be honest with you, tracking asteroids. I'm curious about this 3D. I don't know if you want to share it, Sarah, on the package name.
I'm happy to. I'm trying to remember what it's called. It's for star spot. Let me just star spot visualization. Oh, it's called Starry. Rodrigo here. Okay. Here, I can share my screen so you guys can see what I'm looking at. So Starry has this nice, here's some nice like visualizations of something projected on a sphere.
Sorry, it was away from that.
Oh, sorry. This is, I thought I was putting it over there and I was not.
Thank you.
Yeah. So it's showing like, it's at each time step, it's projecting this model onto a sphere, and then they're making a GIF by like combining many of these. So we can see what they actually use for the visualization. I think I'd probably encourage you to just look at the GitHub. There might be like a plotting or something. Let's see. Sorry. Maps, maybe maps? Yeah, there's a lot of Matplotlib imports here, so I would guess that this is probably where they're actually like doing the plotting. This funk animation thing, that is the thing that like takes individual frames and makes an animation. So I would bet that somewhere in this code there is an actual like, let's see. So if we go to here, so here's an animation. This is the code where it's actually making the animation. Here's a color map, grid. Projection.
And you said it is with AstroPy?
I'm trying to figure out what they're actually using here. It looks like they're using Matplotlib, so there must be something.
Okay.
Yeah, in Matplotlib. I mean, yeah, I should say too, like, I don't know off the top of my head, I haven't made plots like this, but we can like search for it together. I think everybody else is in the breakout room, so I feel like this is a good use of our time together.
Yeah,
Okay.
I added, thank you for this great question. So I'm learning too, but I added just the basic, if you are working with sky coordinates, and either plotting sky coordinates or calculating something between two objects in terms of coordinates or their velocities. There are packages in AstroPy, which I posted the links here.
Awesome. I will share these. Yeah, definitely using AstroPy, I think, just like Maria said, will be super helpful because you don't have to actually do the like calculations of separations and stuff yourself.
Yeah.
And you don't have to worry about like coordinate systems. You can do all that in AstroPy. There's also going to be a dedicated AstroPy lesson tomorrow, an optional lesson, so I'd definitely recommend going to that if you're interested. So here's a spherical coordinate. So this is just making a plot in spherical coordinates, but there also are like nice plots that you can make like on a sphere. Let's see. 3D surface, that's probably going to be the same thing. Yeah, like we don't necessarily want like to plot in a 3D rectilinear space. We want like plot on a sphere. Oh, okay, this looks like a good tutorial. So we've got like we're actually, okay, yeah, this looks good. Cartopy, okay, nice. Python package for plotting map data. All right, that's cool. Yeah, okay, I feel like this is what you want probably. Or this is what I have interpreted of what you want. Awesome. Does that actually answer your question?
Yeah,
or?
that's
Okay,
helpful.
cool.
Yeah, because I'm also thinking about, I guess probably tomorrow's workshop will help too, but also like changing the coordinate system. Like first we show the relative positions from a, you know, like a third person view outside the system, but then also showing you like from the horizontal coordinate. So that means your local view of the sky, like where does this object lie in if you are standing in the observatory's position and you look up the sky at that time, then where are they actually on your sky?
Yeah, totally. Yeah, I think AstroPy will be super helpful. So one of the first one that Maria sent is the sky chord class that AstroPy has. And that's really nice because it basically defines it's an object that defines a coordinate, but it has methods to easily transform between different coordinate systems. So you can sort of like with one line of code transform to an arbitrary coordinate system. So I think that'll probably be super helpful for you.
That sounds good.
Yeah.
Thank you.
Yeah, of course.
So you have just one asteroid you are tracking, or I was trying to understand a bit more the project.
Yeah, so right now we're just looking into like our package is more like whichever object ID you give us will give you a tracking of it. So right now it's just
Okay.
one object per plot, but it could be like used iteratively to have like more. But right now, like on one plot, yeah, just one.
Oh, also,
Okay.
I just saw that someone in the room asked for help. Would you mind going to help them, Maria?
Yeah,
Okay, I can
the
add you to
number
the breakout
one.
room. Yes.
I can.
Okay, cool.
Hi, we had some good back and forth in the breakout rooms. So then, since it's almost the end of the session, please leave the breakout rooms and come back to the main room. So I
Okay.
asked people to come back because we are
Yeah.
at the end. So the breakout rooms I see that are closed. We had really good back and forth in breakout rooms. Please, I will post the answer key. If there are any last minute questions or concerns, comments, criticisms, compliments. Okay, thank you very much. Please post any questions on Discord or Piazza, and I appreciate this opportunity to work with you. I will stay for 5 minutes, but I will mute myself.
Sounds good. We're gonna move on to the Jax lesson in like a minute, I think. I'll just wait a minute in case anybody is coming in. Cool. Okay. Welcome to the Jax lesson, everybody. Jax is clearly gaining popularity in astronomy, as you can tell by how many of you are in this room right now. Last year was the first year that we had a Jax lesson, and I think there were like 10 people. So clearly, it's the word is spreading that Jax is exciting and people want to learn about it. I'm really excited to give you a super quick overview today and let you actually get some practice working with Jax. So Jax is a high-performance, open-source numerical computing library. One really nice thing about Jax is that it has a NumPy-like API. So hence this meme that we can appreciate. Couple chuckles, that's good. Wake up the room. Okay, so there are sort of three main things that we're going to talk about that Jax does today. The first is XLA compilation. So we're going to talk about what that means, what XLA is. We're going to talk about hardware acceleration. So Jax, one of the main advantages of Jax is that you can you can run the same code on CPUs, GPUs, and TPUs. You don't actually have to make any changes. This is really annoying for people that spent like a lot of time learning things like CUDA, which is a library for specifically running things on GPUs, because now you can just do it with Jax automatically. But it's really nice for me that never learned CUDA very well, because I can just use Jax. Another nice thing about Jax is that it does automatic differentiation. So if you've ever worked with like optimizers like scipy.minimize or like MCMC, a lot of these algorithms require you to know to have a gradient of your function that you're trying to optimize. So oftentimes you can't compute that gradient analytically, and so it's really nice when you have Jax that automatically computes this gradient for you. So it enables you to plug into those libraries that require gradients to do optimization without having to like actually compute the gradients yourself. All right, so the first and maybe arguably most important part of Jax is this just-in-time compilation using jax.jit. So compiling in general is something that your computer is going to do to translate code that you've written into code that can be run on the machine. So if you've ever coded in like C before, you might know that compilation in a lot of other languages is a whole separate step. You have to first compile your code and then you run the compiled code. Python doesn't do this. Python will automatically compile it for you. What JAX does is it adds this intermediate step where it compiles into this intermediate language, and then that actual compilation step detects and implements a lot of automatic speedups. So that's part of what makes JAX very fast, is that it does all of these under the hood optimizations. And then the other thing it does is it makes this executable that can then be run on GPUs or TPUs or CPUs. So one thing that, if you haven't heard of GPUs or TPUs before, these are like arrays of lots and lots of, a GPU is basically like a lot of mini CPUs. So you can think of it like 1,000 tiny little CPUs. So one really nice thing about having like an array of lots and lots of tiny little CPUs is that you can do things in parallel very easily. One disadvantage is that individual like GPU like elements are not going to have very much memory. So you have to do this thing where you pass individual pieces of memory to the GPU. It's called loading the GPU. And that process can be inefficient. So the optimization that you have to sort of like think about in trade-off is if I take this piece of code and I pass it to the GPU, that actually might not actually be more efficient if your matrix that you're passing, for example, is very small. It has to be like worth the overhead cost of passing the thing to the GPU for you to actually like, yeah, make it worthwhile. So we're going to explore that a little bit in the activities too. So the other thing is that the compiler is fast, but it also still takes time. Doing this compilation, especially running all of these things that add these additional optimizations, are going to make that code a little bit slower. So a really common thing is that people will start using JAX and they'll say, what's going on? My code is actually slower than it was before. And this is because JAX is not, because you're adding in this whole thing of doing the compilation step. The last thing I want to say is that these types of problems called embarrassingly parallel problems, which are really common in astronomy. So this is, for example, like running the same script on an image like over and over again. So you might want to run on like 7 different images. Those typically aren't going to be very amenable to JAX. JAX was designed to multiply large matrices very efficiently. So like embarrassingly parallel problems, not necessarily good for JAX. But like multiplying a large matrix like over and over again, that'll be a good problem for JAX. All right, so what does just-in-time compilation actually do? So JAX is actually a purely functional language. So this is sort of what Jason was alluding to this morning when he said that his meme was a little bit out of date, that like people were saying, you know, stop trying to make functional programming happening. Functional programming in languages like JAX is actually making this huge comeback nowadays. JAX, this compilation thing, compiles pure Python functions into this intermediate language called JAXPR, which is short for JAX expression. The main thing that it does to compile into JAXPR is it does this thing called tracing. And we're going to talk about what tracing actually looks like. But essentially, you can imagine that when the first time you run your code, if you define a particular function that's going to be JIT compiled by JAX, Python will, as it's executing it, like run through that function, say it's a for loop. The first time it runs through, it will compile it, and then it'll figure out if it can reuse that compiled version. So you don't have to actually worry about like doing this automatic detection yourself. JAX does it for you. So this again is called tracing. And then so that tracing and I forgot what I was going to say. Never mind. Okay, so let's take a look at a little bit of code to see how this tracing actually works in practice. Can you all see the code? Sort of? Okay. So I'm going to give you 20 seconds to read this code by yourself. And then I'm going to talk through what is happening, and then we'll see what it outputs. All right. So a couple things you might notice. First is this decorator on the top, jax.jit. This is the thing that tells Jax this is a function that we want to JIT compile. Defining the function, add one. What this function does is first it prints I'm being traced, then it defines a new variable, y, which is x plus 1. Then it overwrites that variable and then returns this value of y. So the very first time you call add one, that'll be here, Jax is going to trace the code. So it's going to run through, it's going to compile it, and then it's going to store that compiled version for later. So the first time we run it, we're running it on a Jax NumPy array with one element. The next time we do it, we're going to run it on a NumPy array with the same shape, but with a different value. And then the final time we do it, we're going to run it on an array of a different shape. So Jax functions, JIT compiled functions, are they require your input types to be exactly the same, to take up the same amount of memory every time. So this function will get JIT compiled actually twice. The first time with the first shape of the input, and the second time with the second shape of the input. Another thing that will happen is that any side effects will only happen when the function is being traced. So a side effect here is something that will happen that doesn't affect the inputs or outputs of the code. That doesn't affect the output of the code. So this print statement is a side effect because it's not directly changing the output of the code. It's just something that the function doesn't affect the output. So what we're going to see is that even though we're running the same function 3 times, let's now run this. All right. So in the first call, we see we print out this side effect of I'm being traced. So that's telling us that the code that Jax is actually tracing this the first time around. The second time, it doesn't print out that call. So it's using the compiled version. It's not actually rerunning the entire function. It's not using the Python implementation. It's using the XLA compiled version. And then in the last time, it says, oh, okay, I'm running this with a different input now, a different input shape. I can't use the compiled version. I have to recompile it. So now I want to tell you about what speedups we can actually achieve with doing this compilation. So here I've defined this new function, and we're going to return this where, the output of this where statement. Honestly, what this function is doing doesn't really matter that much. Just think about it like it's performing an operation on a big array. You might recognize it if you've done machine learning before. So we're now going to time this. So we're just running this function 2,000 times with and without JIT compilation. The only difference is here we're just using the unJIT compiled code. And then here we're redefining the function as a jax.jitted version. So we're JIT compiling it in one case, and we're not JIT compiling it in another case. All right, so let's run this. All right, so without JIT compilation, 114 milliseconds per loop. With JIT compilation, 113 milliseconds per loop. So because it's reusing the compiled version rather than compiling it every single time, which is also what Python would do, is recompile it every single time, we can get a pretty significant speed up. One thing to keep in mind is that you're not going to see this benefit the first time you run a function. So if you're not going to rerun something, it's going to compile it the first time, and that compilation step takes a while. So here's the same command as what we ran up here, but we're only running it once. And you can see this is going to give us the average time it took to run this command. So you can see the first time it actually took longer than without JIT compilation. And that's because you're not only running the command, you're also compiling it. So you only get the speed up when you're doing the same thing on inputs of the same shape over and over and over again. All right, so JAX has a couple of limitations that are really important to know about. One is that JAX code requires these array types to be static and to be known at compile time. So this is similar to what I was saying before about like every time you have a new array shape, it's going to require it to be recompiled. So here I'm defining some code where the actual output of the code, like which direction, which path it takes through this if statement, is going to depend on the array, on the value of the array. So JAX doesn't like that. It needs the array types to be known. So if we try this, we're going to get an exception. So we get this tracer bool conversion error. And basically the reason is that JAX doesn't know how to trace this. So it would know how to, like Python knows how to run this code because it's just going to compile as it runs through every single time. But JAX doesn't know how to make this intermediate representation of this that it can use every time for every different input because the value of that, like the behavior of the function depends on the input. All right, like I said at the beginning, this really major appeal of JAX is that the API is very similar to NumPy. I think this sort of has like pros and cons. One pro is that you can like use a lot of really familiar NumPy functions really easily. One con is that you might think that JAX behaves exactly the same way as NumPy, which it does not. So I'll show you a couple of differences between like the differences between JAX and NumPy to give you a sense of like how JAX is performing differently from NumPy, even though you can use exactly the same, even though you can use functions that look exactly the same on the surface. Okay, so I've said this, I've sort of alluded to this before, but let me make this a little bit more explicit. So JAX only, a lot of the benefits of JAX manifest when code is written in a purely functional paradigm. So this is what I was saying before, that like your outputs of your code depend solely on your inputs and have no side effects. So you have no like print statements. You don't change the values of any intermediate variables. You like just, yeah, your outputs solely depend on your inputs. So here's an example of some like sort of confusing differing behavior between JAX and NumPy. So take 20 seconds to look at this code, and then we'll run it and try to understand what it's doing together. All right, so here I've defined a function that sorts an array. We have an input of an array that can be either a NumPy array or a JAX array. And then I'm going to run this either using JAX or using NumPy. So in the first case, I input this array. In the second case, I'll input the same array. So what we're going to do here is run this array.sort function. If we do it with NumPy, and then we do it with JAX, let's see what happens. So we're going to print out the library name, the input array, and also the value of the array that's here, this return array. So what NumPy has done is it's actually sorted the array in place. So this .sort method doesn't actually return anything. It just does an in-place modification. So it actually accesses the memory allocated to that initial array, and it changes it, and it has no return. So this return array is none. JAX doesn't do that. It's not able to modify memory in place. It can only allocate new memory, purely functional. So r.sort, even though it has exactly the same syntax, has a very different behavior. R itself, the input array, remains exactly the same as it was input, but then this has been returned to be the value of the sorted array. So this is a source of a lot of confusion when people start using JAX. The way to think about it is that JAX does not like modifying memory. All right. One other like sort of consequence of this is that the NumPy way of like indexing doesn't really work very well with JAX. So for in NumPy, you would use this syntax of like array 0 equals 3, and that would actually access the memory allocated to that array, access the 0th element, and change the value from whatever it was before to 3. JAX doesn't like that. So what JAX will actually need you to do is this syntax. So what this is doing is xold at 0, it's reading that value, and then dot set to be equal to 1. That actually creates an entirely new array and defines it to be xnew that has this new value. So if we run this, you can see that xnew here has the modification, xold remains unchanged. Another weird gotcha about JAX is that like JAX really doesn't like raising errors, so it'll do some really weird things sometimes. So one is that if you try to do access so in NumPy, if you try to access an array element that's out of bounds, it'll throw an error, but JAX will not do that. It'll just like look in that value in that memory slot and just return whatever it sees there. So you can get total junk. One thing that you can do to work around this is you can use this .get and use a fill value of 12. So that says like, if there isn't something there, fill it with this value that I tell you. Mm-hmm.
Why would it be written that way for indexes to work with, like, to not throw an error, I guess, when you're out of bounds? Like, what's the point?
Yeah, I think in general, like throwing an error when you're on an accelerator is really difficult. So it's just trying to not throw errors as much as humanly possible.
Okay.
Yeah. So if we try to, access the 11th value of this 10 element array, in the first case, it'll just give us whatever it finds there, which in this case is 9. If we try to use this, if we try to do that same thing, but we then use that .get value and fill it with this 12, it'll just set that to be equal to 12. So that can be helpful. You can fill it with like nans, for example, if you want to make sure you catch issues like this. There are a couple of useful higher order functions that you can use in JAX. I'm not going to go through these in a huge amount of detail. I just wanted to make sure that you're aware of them. So grad is this thing you can use to automatically compute gradients. And then vmap is a nice thing to do some vectorization and batching tools in JAX. You can read through those on your own. All right, so the main thing I want to let you do with the remaining 35 minutes is get practice running JAX on GPUs and TPUs and comparing the performance with and without JIT compilation and with running on GPUs and with running on CPUs. So a really nice thing about Colab is that you can actually change your runtime type, so like just easily change from a GPU to a CPU. The way you do that is runtime, change runtime type, and then you literally just click what you want. So if I want a GPU, I'll just click here. It's going to disconnect and restart it as if you restarted the notebook. And then you can rerun everything that way. All right, so I'm going to give you about 30 minutes to start going through this. I encourage you to take like maybe 10 minutes to work through it on your own and then form groups to start going over it with group mates. Here we go.
Sorry, can I ask you? Sorry, I think I missed something in the
Every time I'm
beginning,
gonna have
because I thought you were saying like, when there are side effects, like a print statement, it's actually good for JAX because it doesn't like repeat them and somehow it saves time. Maybe I was misunderstanding, but then later I thought you said you can't have side effects, you need like a pure something to use for JAX.
Yeah,
Am I
so-
mixing something up?
It's not necessarily that, I think I maybe misspoke. It's not necessarily that you can't have side effects, it's just that they won't actually, so like the print statements will only be executed the first time it's tracing.
Oh,
Yeah.
which might not be a good thing.
So
Yeah.
you shouldn't have load-bearing side effects.
Yeah, exactly. Yeah. If you want to like, yeah, if you require printing for like debugging, for example, that's not a great idea.
So would the same apply to writing the file, for instance?
Yeah.
Okay.
Yeah. Anything that like you want to be done, yeah, consistently.
Got it.
Yeah.
Starting to understand why MC probably doesn't use this.
Yeah, MC is also much older. Jax is probably like about, I don't know how, Jax definitely hasn't been used in astronomy for as long as MC has. It might be like technically as old as Jax.
Has anyone come up with a way to fix the embarrassingly parallelizable problems? Because I've got a few of those.
Yeah, so embarrassingly parallel problems are a like really common thing in astronomy. It's not a bad thing. Like we want to be able to like run the same code on images over and over again. I think there's just a whole different set of tools, and it's worth like understanding that JAX is not necessarily like the way that we want to go for those types of problems. But like something like even just like GNU parallel, which is like running, like spawning different instances from the command line, that's a really good tool for like these embarrassingly parallel problems. Yeah. Good question.
Sorry, if you want to run your code in a Jupyter Lab notebook or on VS Code, then how do you switch between GPU and CPU?
Yeah, so on the Jupyter Notebook, sorry, in Colab, so it's also worth understanding, so Colab is actually running in a virtual environment. It's like not
It
on
is
your,
the cloud.
yeah, it's in the cloud. It's not actually on your computer. So because of that, and because it's hosted at Google, you can just like choose which backend you want to connect to. On your own computer, you don't have that much choice, so you're limited by like what hardware you have accessible to you.
Okay.
So your like machine might not have a GPU.
Right.
And
But if it has, then what should we do?
yeah, if it does, then you can set up. I'll send you some like there's some setting where you can like tell it what to use by default. Yeah.
Have you ever needed to do that?
Yeah, I do it on a cluster generally, so it does it automatically. Yeah. I actually don't know what the default is.
Is it a big problem with JAX, the amount of memory that it uses? Because since it creates something new every time, I imagine that might be a problem and you need to be aware and delete some of the variables or something like that.
Yeah, that's a good question. I haven't honestly run into a bunch of memory issues, but I'm not sure if that's like, not sure if that's just because I'm not using it enough. So I think just because like you have to create a new array doesn't necessarily mean that like JAX is less memory efficient than NumPy. It's just you have to be aware of like how memory is actually being used. Also, like if you want to use JAX for like a problem where you're like, just changing one particular matrix over and over again, JAX might not be the best choice. Generally, the types of problems where JAX really excels is when you're going to be like, creating a new array and then like discarding the old array or something. Yeah. I guess maybe the thing I should have said in answer to your question is that JAX is, I don't think, any less memory efficient than NumPy. So you can easily run into memory issues, but I wouldn't expect you to run into more memory issues than you would with NumPy. So if you're going to create a 100 million array matrix, you're going to run into the same issues. Yeah. All right, we've got about 20 minutes left, so I encourage you, for the folks in person, to turn to the person or two next to you and start talking through some answers. For the folks online, I'll open some breakout rooms. I think there's probably just going to be one breakout room. All right, I'm going to just briefly talk about the point of the activity, what I wanted you to hopefully learn. Please don't feel like you should have finished. This is a long activity, and basically the point of this was for you to just start thinking about this and not necessarily to finish it. So feel free to keep working on it. We'll also post the answer key later today, so you can compare your solutions against the answer key if you want. One thing I realized I also didn't really talk about was the difference between GPUs and TPUs. I heard a couple of mutterings about that. Jason doesn't believe there's a difference. So JAX's TPUs were first manufactured by Google, and my husband works at Google, and I did an internship at Google, so I've kind of drunk the Kool-Aid, and I'm like, TPUs are a whole other thing, and Jason's like, it's literally the same. But both of them are basically like these like things that can do lots of stuff in parallel. The difference is what they were designed for. GPUs are called graphics processing units. They were designed to basically run video games. So they want to be doing like many ray tracing operations in parallel. TPUs, on the other hand, are tensor processing units. They were designed for training machine learning, neural networks. So those are really good at matrix multiplications needed for like gradient descent, stuff like that. But yeah, you can think of them as basically they're the same thing. They just have slightly different optimizations. Okay, so this is the function that I wrote in order to test the performance of the SELU and SELU-JIT function connected to a GPU and a TPU. This is not necessarily the best like software development-y way to write this. I think probably if I were to do this again, like one thing that's like some not a great practice of the way that I wrote this is that this function really depends on the state. So it depends, it's going to perform differently if you're connected to a GPU or a TPU. So one way that you could potentially get around that is by writing like separate notebooks, one that only does something when you're connected to a GPU, one that only does something when you're connected to a CPU, have them both like write out their answers to like a data file, and then have a third notebook, for example, that reads in those outputs and plots them versus each other. But that's what I did when I wrote this answer key, and I didn't have time to fix it this year. So this is what you get. So you can see I'm making a plot. I'm first defining arrays of different lengths, and then initializing these arrays that I'm going to store the times that it took to run both the JIT compiled and the not JIT compiled version. Then I'm going to create an array of all these different array lengths. Note that this is exponential, so I'm creating arrays of length like 10, 100, 1,000, all the way up to 10 to the 7. Then I'm running the non-JIT compiled version, then I'm running the JIT compiled version, and then I'm updating the values of these arrays. So also note that like this function is pure Python. So you can write Python and JAX together, which is a really nice like thing that you can do with JAX. So if you want to like run all your heavy lifting calculations with JAX and then just use like regular old Matplotlib to plot your results, you can do that. So I'm first going to make the runtime plot connected to a CPU. So this is what it looks like. So the first thing you might notice, aside from the fact that there's a little bit of like random noise due to whatever was going on with the machine at the time, there's this overall like exponential increase. And that's just because as my array length gets longer and longer, it's taking longer and longer and longer in an exponential fashion to actually run this code. You can also see that there's basically a constant offset between JIT compiling and not JIT compiling. So JIT compiling is like a constant time savings. Whereas it'll not necessarily like, make your, I'm going to use O of n, but your O of n cubed code be not O of n cubed, but it will introduce this constant offset in time. The GPU, on the other hand, looks like this. So we see the same constant offset, but you can see for these much longer array lengths that the runtime is approximately constant. So I probably should have plotted these on top of each other. One thing you might notice is that like for the smallest array lengths, running on the GPU is actually less efficient than running on the CPU. So the GPU line is about here. So you only start to see the advantage of the GPU when you get to really large array lengths. One other thing to note is that this wouldn't like work forever. It wouldn't stay constant to like infinitely large arrays. At a certain point, you're going to start overloading your GPU and having more operations than the GPU can feasibly perform. But this is the main advantage of GPUs, is that once you subtract out the time it takes to like put your data onto the GPU, which the code does internally, it then gives you this like constant time savings because it can run things in parallel very easily. All right.
So then if we were to extend the x-axis to infinity, would we just eventually see the same exponential growth?
Exactly. Yep. And that's where you would start overloading the GPU and you'd start having to run things in like multiple batches on the GPU. Yeah, good question. All right. Thanks for coming, everyone. We'll see you tomorrow. Hope you had a good first day of Code Astro.
Thank you.